In this video, we will be looking at the solution to section 8 from the 2016 winter exam. We have a model that predicts the fitness of a species, and that'll be our F value. And the idea is that species can choose how they want to spend their energy, and one of the ways they can spend it on is reproduction, so having more children, more offspring, or they can spend it on survival, so keeping themselves alive until they can potentially reproduce. One of the ways we can model the impact of both of those values on fitness is to build a function, a mathematical function. And here's one model of it. The number or amount of energy we spend on reproduction to the power of 0.4 times the amount we spend on survival to the 0.6. That combined number gives us how fit the species is. Higher numbers would be more fit. Now, in principle, we could put as much energy as we wanted to and into either reproduction and or survival. And so if we had both of those being just positive values, do we have a global maximum for this function? Well, the answer would be no to this, because as r goes to infinity, as long as s was positive, as r goes to infinity, the r to the 0.4 is going to go to infinity, because it's just a root of that, and it's not 8, it's infinity. And what that means is that our fitness is going to infinity. Now, if our fitness goes to infinity, there can't be a global max. A global max is a single highest point, be a global max. A global max is a point which is higher than all the others, but if our function keeps shooting off towards higher and higher values, there's no stopping point, there's no single point that's highest. So that makes the question, why do we look at this fitness if in principle the fitness can be as large as we want? Well, then we throw in the real world constraints and we see what happens with that. Suppose now that a particular animal has a total energy of 4 units, and what it can do is split that energy between the two aspects of reproduction and survival, and we even provide it here. Reproduction plus survival energy use has to add up to 4. And as soon as we see that, we should be feeling like that's a constraint, and we're going to be using, yes, the Lagrange multipliers to identify the energy that's going to produce the highest fitness value. So this is a perfect application of our Lagrange multipliers. We have our f function, that's a function of r and s, r to the 0.4, s to the 0.6, and we have r plus s equals 4, and that combination fits perfectly with our Lagrange multipliers. This is our little f function. We're going to use r and s instead of x and y. This is our little g function of r and s, and this is equal to some k value. So now we just build our Lagrange multiplier equations. Those are, I'll write them out in long first, the r derivative of the f function is going to be the same as the r derivative of g, except with a multiplier. The s derivative and the s derivative are the same, except with a multiplier. And our g function has to equal the constant, or has to have the constraint satisfied. Now we can fill in the blanks. The r derivative of the f function, this is our variable. We have a power, so we take the power down front, and we subtract 1, that'll give us negative 0.6, and then times s to the 0.6 left over, equals. That is our fr. Now the equals lambda, some scaling value, and this part's easier. The r derivative of g is just 1. Repeat on this side, this time with the s derivative, so we'll have a 0.6 out front. R doesn't change, but we differentiate the s, so we'll have s to the negative 0.6 equals the s derivative of this g function again. Well, that's also conveniently 1. And last but not least, r plus s equals 4. Lovely. So now what we can do is number these equations. And for this kind of structure, one of the nice things we can do is just take 1 and divide it by 2 on both sides. The reason that's nice here is because we have lots of powers with the same base. And if we're careful, 0.4 over 0.6, that's the same as 2/3. r to the negative 0.6 divided by, so imagine doing this, r to the negative 0.6 divided by r to the 0.4 gives you r to the negative 1, or 1 over r. In the opposite scenario here, s to the 0.6 divided by the negative is a double negative, that's s to the positive 0.4. So we get s to the positive 1 when we're done, and the right-hand side is just 1. Do a quick erase. That should have been a multiplication sign there. There we are. Well, that's not too shabby at all. Here we have s and r in 2/3, so we can actually say that s is 3/2 of r. And that's nice, because then we can just sub that into our third equation, and we should be able to solve for one of the variables. I'll put that into 3. We get r plus s, but s is the same thing as 3/2 of an r. That adds up to 4. 5/2 r equals 4. And that gives us r equals 8 over 5, which is approximately 8/5. It's not approximately, it's exactly 1.6. And going back to the other values, our s then is 3/2 of r. Or you can go back to this formula. They're all consistent now. So we'll have 3/2 times 1.6. 0.8 times 3 is 2.4. And notice they do add up to 4, which is perfect. And so we have our r value, which was 1.6. We have our s value, which is 2.4. And we were asked to find the optimal fitness. So the fitness at r equals 1.6, s equals 2.4 is going to be 1.6 to the 0.4 times 2.4 to the 0.6. We're just using this formula here with the two values we found, and then we go to our calculator to resolve this, and we get a value of approximately 2.041. Now we don't know the units of those, but it certainly is a number, single value, that we can apply in this scenario. And what we do have confidence in is that the value we just found with that r and that s will give us the highest value for this function. Why is it the highest? We don't have a critical point analysis we can do here, but given the scenario, we want to make r and s as big as possible to make f big. That's kind of what A was pointing at. But within the constraint, we would like to have a little more s because it's to our advantage to have a bigger s because it has a higher power. But we can't let r get too small. So some kind of compromise like 1.6, 2.4 balance seems like a reasonable option for the highest f value in this scenario.